All right. Am I live? Okay, cool. Yep, I see my message popping up. I'm gonna ping the Discord group that I'm live. Hello from Jamaica. Oh yeah, I should post the Discord link again. Because people always ask for it. It should just show up in it's just public again. So this same link should work every time. There's the invite link again in the chat. Wow. All right. I think the other. Yeah, we had looks like the other plugin decided to start working finally for the overhead display on the screen. Yeah, that wasn't working this morning. I don't know what was up with that. Gonna of course give it another 6 minutes before we get started. I'll get to the questions at the start here in 4 minutes. I'm still kind of reading through some stuff. There's going to be a lot of stuff we go over today. It's not going to be just collaborative filtering and content-based filtering. There's a little bit more to it than that going on today. But I'll get to your questions though in a few minutes here. Okay, it is 3:15. We are good to go ahead and get started. So this is going to be a really tricky one. I've done a lot of reading on it. Let's go through the chat comments though really quick. The first question is, could you go into mini ML, inference and system design, advanced topics for data structures, algorithms, etc. for this one? Please assume advanced level skills for audience. It's going to be tricky. It's going to be quite a bit. I'm not going to do a lot of hand holding. I think I'm going to assume that people know the difference between clustering and classification here. It's actually still it's going to be interesting. It's going to be a journey. I'm going to redo a couple of specific cases of a recommendation engine probably over the next few weeks. That's in my agenda. This is going to be the broad overview. People might correct me afterwards, but we're going to do a lot of really deep approaches. We're also going to do, so we're not just going to do collaborative filtering. We're going to do the item based approach, and then we're also going to do the user based approach, which I don't think is really used a whole lot anymore. It doesn't seem like this is really popular. We'll talk about why, and then we're also going to do the whole candidate generation and God, what's the other one? Ranking approach. We're gonna do that. We're gonna talk about like why and some trickery that we can do with that. I should maybe even get into a couple of examples. Let me get to that other question, and then I can go ahead and start talking about this a little bit more. I don't even know if I would call this variation. So there are different problem variations, but they're going to be in their own videos entirely. These are kind of like approaches. They're different types of recommendation engines that you'd make. This video is almost, the title is almost a little tongue-in-cheek because somebody else made a video called design a recommendation engine, and you don't, there's not one way to do it. There's like I have here at least three or four different ways to do it. It's not one. Anyways, could you clarify when to use a queue versus a stream? Queues are when you're okay with losing the data going into the broker. Streams are when you definitely want to hold on to it. A queue is like, so for example, if you don't really care about a message getting dropped, while on the other hand, another piece of it could be the volume that you're working with, the traffic volume. If you're not measuring your traffic in terms of TPS, you can go ahead and just switch over to a queue, and it might even be easier to set up because it handles the fault tolerance internally. A queue is for when you, so for example, if you're only getting like 10 calls per hour, that's what I meant by like not using TPS as your metric. If you're getting like 10 calls per hour as opposed to 1,000 per second, you might be able to get away with using a queue. And then for streams though, it's like if you're handling more traffic than you can hold on a single node, on a single machine, you're gonna need to use Kafka. You're gonna need to use a stream. Those queues are not typically meant for anything that you can't fit on one machine, to my understanding. They don't really horizontally scale out. Kafka can be sharded. I don't think queues can really be sharded. And if you're going to try and do anything like that, you'd be better off just going ahead and using Kafka. It's a lot better for that. But Kafka does a little less handholding. It doesn't internalize the fault tolerance like with queues. So like with RabbitMQ, if your consumer picks up the message, or I guess even with Redis PubSub, it'll just go ahead and push it out for you. But with RabbitMQ, if you pick up the message and then you don't tell it like, hey, I handled it, you're free to delete it, RabbitMQ will try again with a different consumer. It'll assume that you screwed up, and so it'll hold on to it. So it's a little bit more friendly to work with queues, but they don't handle high volume, and they're less robust. It's in general, huge traffic volume, you want to use a stream. Okay. I'm going to skip those two. We're going to go ahead and start diving into this. So content-based filtering. So this is generally going to be, as an example, one case of it would be if you're trying to, it's for like if you're on a website without a user system, if it's like a news website, so like CNN or a blog, and you've not really interacted with it at all, but it still is trying to recommend similar articles. Maybe you've clicked on like one or two different links on Quora, and then Quora is trying to recommend a bunch of other similar questions on the sidebar or something. Stack Overflow might do that. Stack Overflow might take an approach of this, or a blog, and recommending other blog posts. I did something similar to this in college. It was kind of like, it wasn't even intended for a specific user. I guess there are ways that you can do this with classification, but the way I did it was with clustering, and it relies on let's go ahead and make a little note here. It relies on, you have to like your model has to understand like what the objects are. It has to like you have to do feature engineering. So if it's like an article, it has to be able to figure out what the article is about by like looking into the words of it. But with collaborative filtering, you're not gonna try and figure out like what that article is actually about. It's not gonna try and do like IDF/TF. So it relies on feature engineering, like I think people actually usually call it TF IDF. I heard it IDF/TF when I was in college. So you have to like actually do some kind of feature engineering there. While with collaborative filtering, you're relying on similar users. Relies on similar users is that one, and you don't have to do any kind of feature engineering like that. There might be, I guess in some of the problems I looked at, it looked like you kind of could do something like that. It was really weird. With this one, I saw more cases where you would still maybe try and like figure out the content, but it was as like the second step. So they do like content-based filtering here. Oh, this one was collaborative filtering. Yeah, it was weird. So this one's most known from Amazon.com is a great example of that. And I'm gonna cover that sometime in the next few weeks, in the next like month or so. It's on my agenda already. So Amazon.com's similar item recommendation, they kind of like invented that. They kind of invented that, and it does actually kind of use similar user information. You don't necessarily have to know what the item actually is or try and like figure out what's in the description of that item. You can just look exclusively at the user item interactions, and I'm going to write that down. That's a really important term for working with collaborative filter. Is you have users and then you're going to have items, and that's what this whole thing is. Item interactions. That's what this whole thing is going to revolve around, is those two terms. Those are our key entities here, users and items, and the interaction is going to be something like a rating, like ratings. So like thumbs up, thumbs down, maybe 5 stars out of 5 or 4 stars out of 5, like what Amazon.com has. And then this one's old. This one is it's not really done a whole lot anymore. I don't know if anybody actually uses that anymore, but it usually, so what they'll usually do is they look at the K most similar users, and then they have, it's when you have more data about the users than the items. And that's pretty rare. That's pretty rare that you have a lot more data about the users than the item. So it's when you have like you might have just 100 users, but you have millions of items. So yeah, there's that. And then this is when this is some kind of trick for scalability. We are going to talk about scale today. That's not something that comes up. That's what separates machine learning system design from just what you learn in college about classification and clustering. That stuff is boring. Where does Feature Store fit in recommendation engines? I would recommend checking out Chip Hoyen's book for that. So she actually has a little piece about feature stores. Another great channel, there's actually this channel, it's mlops.community on YouTube. I think it actually has like a 5-minute video explaining what a feature store is. So that's a good one. A feature store stores offline features you want to add into an inference based on a user ID from the request. It's you have to know what a feature is in machine learning. It's one of the columns in the table that you might be drawing. Okay, let's go ahead and keep going because somebody requested this is for advanced users, and that was kind of my intention as well. So features is also kind of it's kind of a very core basic concept in machine learning. Okay, let's go ahead and try to start with a content-based recommendation engine where you've just got this like some kind of blog, and you don't really require the users to log in order to read the blog. So Business Insider's ruled out. I think Forbes is ruled out. Wall Street Journal, New York Times, throw those ones out. It's probably, I guess, Medium.com, or I guess there's a lot of things hosted on Medium.com. Maybe they have a little bit more data mining on you and they can actually kind of fingerprint you. Anyways, we're going to go ahead and cover those two core requirements is user interactions, and then recommend some items to a user. And so the first case is kind of not really going to apply for our first variation or approach here, which is going to be content-based filtering. Content-based filtering. Okay, so you've got, we're going to say that we actually have uploaded items. These are news articles in this case. And then you're going to have user interaction, and you're going to have user recommendation. Recs. There we go. Get user recommendations. There we go. Okay. So we're going to need our backend services. This is going to be the upload service. This is kind of like a little beyond the scope that we need to actually handle, but just for the sake of giving a good picture of the whole thing. Interaction capture service, and we're going to have the what is it? Recommendation service. So we call it get recommendation service. Okay, and so you're going to have this content that's probably getting served up on the page. Yeah, you're going to have this content that's getting served up on the page. So this is like the content DB. These are going to be the items. And this is a OLTP database. That's really important here. We're going to be playing with some OLAP data for sure. So let's say that maybe a journalist wrote an article, and it's got to be hosted somewhere. Maybe you'd even pull it down. You could even have this, I guess, on a CDN. It doesn't even have to be on the database. You could have it distributed worldwide too. So there could even be the content CDN. I'll probably even make a simplified diagram after this to kind of omit this extra junk, but full picture on this thing. Okay, and so you can kind of push it to, so you can push it to read replicas, and so CDNs are really kind of like a read replica. All right, and so you've got this user, and he's trying to view some content. He navigated to your website, and so he is going to pull your article down from the CDN. It's either going to be there, or if you don't even have a CDN, if it's just off of one machine, if it's your own Jekyll server, you just run it straight off of well, I guess even with Jekyll, it's just HTML files. But with Jekyll, if you're doing Jekyll, you're not going to have your own recommendation engine rolled on it. So yeah, so you got the page, you've loaded up this page, maybe you click the like button, and so that would be an interaction. So you've loaded up the page. Actually, you know what? I totally put that diagram, should go third. That should be over here. So you've loaded up the page, and now you're going to interact with it. So there's the interactions. Oh, when you load up the page, there's also recommendations. Okay, so you load up the page and then you're going to have recommendations on that page. So next you're going to go ahead, so you've loaded up the page and now you're going to get recommendations on that page. So how's that going to work? So we got the content, and we're not basing it off of the interactions in this case. We're going to need to have, so for all of our content, there should also be some kind of OLAP version of it. We're going to need a data warehouse. It's just this big dumping ground of tons of hard disks. Yeah, we're going to make it big. That would make the most sense. A data warehouse is just this cluster of ambiguous servers that you can dump your tables on, and you don't think of those tables as individual, horizontally scaled out things like you do with OLTP databases. They just kind of blur together on a data warehouse. So that's why I was like, it can kind of be like big. So you have your content, your items over in the data warehouse. You're going to need to go ahead and transform them. You're going to need to do your feature engineering. You're going to need to clean them up. I'll get to your question here in a minute or two. I'm going to go ahead and try to finish my train of thought. So you got your content. You're going to need to do IDFTF. And so we're just going to go ahead and do this. So you just kind of like transform the table into a new one. And I guess that could even be done in Spark. You're probably going to do a lot of your transformations with some kind of worker machines. You would actually do something, you do like ETL work. So with Spark, I believe you pull the data off of the machine and you do it on the Spark workers, as opposed to Trino or Dremel, where you would actually do it in situ. And then, so if it's Trino or Dremel, you're actually able to do it directly on the data warehouse, but those are for really small queries where you're not doing a gigantic feature engineering transformation of a full table. It's for when you want like a couple of records. You're not going to do anything that's going to take an hour to run. For our feature engineering, it might take an hour to run. It's going to do a lot of crazy stuff because we're trying to make our proper, comprehensible, like structured data. We're taking the unstructured content items and returning them into structured data. So we have some Spark workers. Okay, and they're going to do inverse document frequency, term frequency. There, come on. And whatever other feature engineering is going to need to happen. So in my case with CNN or whatever articles it is, it's not really going to involve, it might not involve a lot of joins, but in some cases when you're doing content-based filtering, it might involve really pulling apart a lot of features. So like, for example, if you're trying to do content-based filtering on movie files, I don't know why you would want to do that. That would be horrifically painful. Oh, I guess if you're trying to do music recommendation, you might try and engineer some features out of your MP3 files. So Spotify might try and do something like that. Spotify might try to do a little bit of content-based filtering. I mean, they'd probably have a little bit more user interaction, but there's probably something that they're going to do with content-based filtering somewhere within their pipeline. All right, so you got your flattened table, okay, and now we're going to want to do clustering. We're going to have our item, and we want to map it to the most similar items. So you're looking at some article right now, and on the right, there's going to be some recommended articles that are, it just is like, you have to encode this training thing, the model, to be able to figure out which articles look the most similar. We don't have any user interaction data to work off of. That is going to come later. in other variations. So you just get the articles and that's all. And so given this gigantic set of articles, you have to recommend the other ones. And that is the model. So we're also going to have a worker for training the model. So these are going to be model training workers. So if you ever heard of like how Google or whatever it is that is, they have all these like GPUs for training this massive neural network. That's going to be these machines right here. They're probably going to have some GPUs strapped to them or something. You can actually do distributed training, I guess. That's what I'd read. I've never tried it because I've never had an excuse to try and do anything like that. I know it's going on somewhere near what I'm working on at my company, but yeah. So you're going to train, you're going to pull the data in, actually, yeah, so you're going to pull the data in, and you don't need to actually put it on the data warehouse. This is actually where that thing called a model store is going to go. Actually, I guess the feature store would be where this thing would be pointing. The feature store is where this would be pointing probably. I guess we could go ahead and pull that out. I'm not super familiar with feature stores and model stores so much as just working with data warehouses in general. Yeah, but I guess we could, I definitely think we want to have a model store, and it would be, unlike a data warehouse, it'd just be an object store like S3 or HDFS. It just needs to store objects and files, as opposed to a data warehouse where it's columnar storage. So you train the model, you're going to serialize it into something like a pickle file. That's what you get in sklearn. You can serialize your trained model into a pickle file so that you can actually reuse it and stick it on different machines without having to remake the whole model. And so then this model that you've trained, it is going to get deployed onto the service over here. It's going to have a data model. And we're going to draw it like that. I'm going to stick it right on there. Okay. And so you would deploy this. So when you're running deployment of your service, whatever you're doing to make that deployment happen is going to also pull in the data model and stick that in a sidecar deployment directly onto the service when you're deploying it. And we're going to label that service deployment. Sidecar in service deployment. And so you would pick up that model when this thing starts up so that it'd be able to start servicing requests. It would pull in that, pull that model into RAM in the same way that would pull in or set up a database connection. It's just you have a little bit of code during the service initialization. It's just like, hey, there should be this model here. The file is located on your disk right now. It was put there during the deployment process, so just like read it into RAM, and you're gonna hold a reference to it, and I'm gonna like throw stuff at it in some function calls. And this should not be extra large. Let's make it there. That'll do. Okay, I'm gonna answer some questions, and then we're gonna kind of vary this a little bit. Yeah, I think you can actually do this a little bit differently. But I should also say that this was doing clustering. You're clustering the documents, and so then yeah, I heard there's other ways to do this that involve classification, but yeah, I'll go ahead and get into that. I'll go ahead and get into how I think the classification would work here. I don't really trust that because it just seems so horrendously complicated how you would actually make that work. and yet content-based filtering seems like it's supposed to be the easier approach, or more primitive or something. There's ways that you can make it more complicated when you do the two-step process, but just as this, it's I'm just not buying it that the classification would make that much sense there. Okay, questions, right, questions. Where does feature store fit in? You already answered that. What kind of item / content is this use case about? So we're just doing articles. We're just kind of doing like news articles, like CNN or like a medium.com blog. So when you're on like Medium, I'm fairly certain that if you scroll all the way to the bottom of whatever you're reading, you're going to see these other article recommendations for like blogs run by some other people that are not the same author. Some of them might be by the same author, but some of them are going to be by different authors. But like when you're on that, you don't even have to you don't even have to log into medium.com and it'll do these recommendations. So you don't even have a user account. You just roll up to the site and it immediately has content, like it just immediately has recommendations for you, even though it doesn't know who you are. And the way that it does that is, well, so there's that. Content-based filtering. So that's if it doesn't have any kind of user system at all. So this is kind of where I'm imagining the way that New York Times used to be, like before they like really got serious with their paywall. Maybe smaller newspaper outlets would do something like this, although they probably have it like outsourced to something. But like you log in, you're looking at some article on some who knows what newspaper that you've never visited before on the internet, their website. It just immediately has recommendations for you. And one of the ways that it can do that is content-based filtering. It just kind of like knows what similar articles there are to the current one without having to look at the way that the users interact with the different pages, as opposed to item-based filtering, which is what we're going to do next. But first, well, okay, let me finish getting through these comments. One model per user. So that is where I was going with the classification. Looks like there is one model in total. So for clustering, yes, there's one model in total. Yeah, I can go ahead and elaborate on this. Sure. So clustering, there's just one model in total. And then if you're doing classification, I think you literally have one model per user if you go with that approach. Because it's not doing similar user, it's not able to look, it's not supposed to look at similar users to determine what to recommend to you. And so it actually builds a classifier specifically for your interactions alone. It can't really, it doesn't, it's not supposed to look at similar users for content-based filtering. It has to work off of features that it has like pulled out of the things that the items that it's working on. Okay, so with clustering, I'm going to do a second approach to this one, and this I'm going to go ahead and like cross these out. You're not actually going to use interactions for content-based filtering. Come on. My computer is really slow today. Okay, so we got that. I wanted to simplify this a little bit, and then we're going to talk about an alternative approach to what I just drew that might be a bit more efficient. You don't technically need to have the CDN in there. So this is what it would kind of look like usually. So you're just pulling the article. Oh, that is you're not going to call it a database directly from your browser. That would be ridiculous. This is the view article service. So you make a request here. Show me the specific article that I'm on the web page for right now. Show me the content that the journalist wrote for it. And we're gonna get the response back. And then we would get the recommendations, or that could even be done directly on this. It can be inline and handled server side. I think that would be a massive pain in the ass to try and do a server side render of those directly into it. Yeah, I guess you could. No, yeah, I just think that would be incredibly painful. Okay, so slightly simplified. Okay, and now we're going to talk about a pre-computing approach. So this one is slightly simplified diagram. I'm just kind of getting rid of the CDN over on this one. Then over here, we're going to call it the pre-computed approach. Okay, so when you do a cluster, the model's not really going to change. It just has these like little sets of the IDs of like the things that it clustered. So it just like has these sets of the article IDs. And so you can just have each one map to a list of all the other ones. And so you could even just have, I guess the way that you could even write it is, should look a little bit like this, where you have like a post ID. We're going to say that it's post number 3456, 3467. They add over 3,000 posts on there. You're doing the clustering, and so you're going to have actually we'll have the cluster ID over here. Cluster ID, because it put it into little sets. We're going to say that there's 20 sets of articles that it has made. Actually, that's probably low. It'd probably be like a few hundred. We're going to say this one's cluster 19 though, and then there's another one in that cluster. We'll say that it's article number 3560. It's also in the same cluster. And then you're going to have these other ones that are in like, let's try 3780, and it's in, let's say, cluster 5. So the data is going to look kind of like that. It's going to be pretty, it's not going to change a whole lot. It's not actually going to change at all depending on what the post ID is under this scenario. So you don't even really need the model. I think you can just go ahead and translate it directly into these like mappings where you can go ahead and you would tell it the cluster ID for your current article, and then you could just go ahead and do a select star from cluster table where cluster ID equals 19, and then it would fetch all the post IDs, and then you can just build links for that. And so you would, like, if you need, I don't think you would actually need DynamoDB for this. I think this would probably fit on a single machine. Maybe you'd have read replicas or a synchronous read replica just for redundancy. I don't think you would really need to have DynamoDB for this. You can totally just get away with PostgreSQL. So you're just going to have a primary key. If you did partition it for whatever reason, it would be the cluster ID that would be the partitioning key. But you're not going to need that. Okay, and so you can just go ahead and spit it out like that. You can go ahead and like, I guess you would probably do blue-green deployments if you ever update the clusters. So yeah, we'll call this the cluster DB. It's OLTP. You would probably do blue-green deployments here. You don't want to slap that kind of, you don't want to like run like several thousand writes against this in one hit whenever you're trying to update it. So you'd probably do blue-green deployment there. And then you don't need the data model. It doesn't need deployed. We can go ahead and label the blue-green deployment. Yeah. Okay. So you got your web page loaded, and then you're like, and then it's going to show you the related articles at the bottom by just kind of doing this. And then we're going to go ahead and talk about the classification approach, which is going to be really wacky, and I'm still not 100% confident with that one. They said it's one way to do the content-based filtering approach, but I don't know. I just don't trust it a whole lot. Everything in this everything in this column is content-based filtering. We're just going to keep going down, and then when I get to the next one, I'm just going to stick that in the next column. Okay, so we're going to try this with a classification model now. It has, so it's going to have like a classification model like per user, and you actually will use interaction data, I guess, but none of the other users are going to see your interaction data. So it has some aspect of privacy to it, I guess. I'm going to copy that, and it still counts as content-based filtering though, because you still have to rely on that feature engineering like TF IDF, as opposed to being able to rely on just the ratings themselves from similar users. So it still, that's apparently why it still counts as content-based filtering. So you have these interactions, and so when you click the like button on the page or something like that, it will write to a, actually you're probably going to have it in a stream. Usually when you do a setup like this with interactions, whatever interaction is, so like if it's an ad or something, you're usually just going to grab it on a stream. So you're like, hey, I clicked the like button or whatever it is. I interacted with the page in some way. So it's like, okay, captured. If it is a like button, if it's something on like YouTube, you would actually probably keep an OLTP database, and then you would go ahead and do change data capture like you did with the content DB. But in this case, you can just go ahead and have it written straight to the data warehouse. We're just going to kind of cut corners a little bit. So it's getting in there through a DB trigger for both of those. This one would not be a well, so if we had a database there, it would be a DB trigger. Okay, I want to draw it. I want to draw the interaction DB. Sorry. And you would have a task runner here. I'm omitting it, but yep, you would have that. you know what, we will just kind of like, nope, 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 nope. I know how I'll do this. There. Hopefully you guys have been watching me enough to know exactly what that means when I stick that there. Okay, so we got that. So now we have the interaction data, and we also have the content, the items. So we can go ahead and do our feature engineering. We can still do our feature engineering, and so we have the user features, and we have the item features, and we are gonna try and get some user features, I guess. We're going to try and just from their interactions that we're capturing, it might be just off their IP address. That might be how we're giving them a sense of identity, but we don't really have like a specific user system. You could actually have user features here, but so you can actually kind of have an embedding for the user, but it just you don't compare it with the other user embeddings. You're actually treating the user's features just like they're a document, and so the user's features they're like the exact same columns as the ones for the documents, and you actually try and find the closest documents to that user record when you're doing the I think is the way that it works. That's how something described it to me. Okay. Anyways, hold on. I'm thinking this through. So you have this model. You're gonna serve up a model. It's a user specific model. Let's talk about how that model is gonna work. Okay. So we have item features, and I believe no, why would you have the user feature? Why would you have user features if you're not comparing it to other users? That's why I get so confused with this thing, is that you don't, why would you have user features, because then you are comparing it to other users, I thought. Going to stick it through this model. That's a classifier, and then it's going to give a probability. It's going to give some kind of ranking out. It's going to score that specific item. This is actually my least favorite. I understand the other models a lot more, but apparently you're able to do something with the classification model here. And I've just like never been able to wrap my brain entirely around it. And it's like on a user basis. It's like a user specific model that you're learning. And so I think each one would kind of have so you don't want to be passing that model over the network every time that you're trying to load up the recommendations. Particularly if it's a large model, it should actually be hosted on you should have this stateful service that has the data model on it. And so instead of having we're still going to have the get recommendation service, but there's going to be this extra thing that's going to call, that'll be a horizontally scaled out, I guess we'll call it like the model hosting service. And so this will be stateful, horizontally scaled out, and it'll have the data models deployed to it. And through service discovery, this thing is going to know which of the instances is going to have the appropriate data model on it. So you load up the page, and then you're going to try and get some recommendations for the page. This thing's going to talk to this, which is, it's a little bit like a database. It like kind of functions a bit like a database because it's holding a specific a model specific to a user, and then it's going to run that model locally. It's not going to hand it over. It's going to run the inference locally on the specific instance that has the right model on it. It's going to return. So you're ranking the list of items. That's what's okay. So you're actually ranking the list of items. Wouldn't it need to like get the list of items? You could like deploy it locally to the model hosting service. So you have, okay, does it really just do a full table scan across all of the items? Is that really how that works? That's why I think this is so weird. Is it's I think it's supposed to do it's doing a ranking. It's doing a ranking of. I guess this is called the ranking service. Yeah, no, it's not. That'd be the most accurate name for it. Is that it's a ranking service, but we don't have a candidate generation step here. We don't do like candidate sourcing or like the first one that you see in some of those really crazy looking diagrams. We're not doing a candidate generation step. We only have the ranking, and so it would have to run over the full list of items, which is weird. And so it ranks the full list of items. It gives you the ones that are the most similar. Actually, isn't that nearest neighbor or no? It's not. It's you have. For the classification, you can do like naive Bayes, or you can do what was the other one? A decision tree. Oh, that would make sense if there's a really low number of items. If there's only like a few dozen items instead of like a few thousand, that would like totally make sense. And then you could just go ahead and cache you would just have like a item store cache. So doesn't this one make more sense if it's this is when you have basically no data on the users. All you have is the items, and you have domain knowledge of the items, and you're able to extract features out of them. You could have a co-deployed Redis instance that has your full item store. Or like it's the what is it? It's embedded. It's the embeddings of the items. It's item embeddings. It's just Redis. That would make sense. Otherwise, I have no idea how in the heck they're doing that. So in your service deployment, you're also going to then be getting a copy of this off of so you don't want to actually copy it straight from LLTP, so you'd probably pull it through a copy that's off in the data warehouse or something. Yeah, so we could do something more like this. Yeah, so this was one of the ones that I was doing a lot of reading for leading up to this. Is I guess this is one of the ways you can kind of do content-based filtering. This is going to look a lot more. This looks a lot more reminiscent of like what you would see, I think, towards this last item right here, where you're doing the two-step process, because usually that's where you would have the much more crazy-looking ranking service that actually has a classifier in it. And like user features. So you do have user features. Okay, and you're also FYI gonna have classification right here. And I guess it would probably be rather live. You might train it rather live and continuously deploy it straight over to there. So that's like a reinforcement learning thing, is that this thing is going to want to react more quickly to any kind of interactions coming in. I think we can put that off to later in the process. This one's already so crazy, and I actually know stuff about some of the other approaches. Okay, let's get through any questions you guys still have, and then I'll move on to the next variation. I'll move on to item-based collaboration. Okay, looks like more than one. Advantage of feature store is you can use it for both training and inference. Yeah, yep, that sounds about right. Yeah, so you use it so that you can you get the embedding off of the feature store. It has like the user's normalized, regularized features. What model are we training here? That is a really good question. Come on. All right. Here is the question. Nope. No, it's not. Oh, God. Thank you. Oh, Jesus. Okay. What model here? So for the clustering, I've had the best experience with, actually that is a really great question, because there's some clustering models perform really well, like dbScan. I think that one is big O of N, or it might have been Birch. It was either dbScan or Birch is big O of N. I haven't really touched this, and I don't do this like day to day of my job. So I don't actually have to know this stuff myself. But I know there's some kind of clustering model out there that is like big O of N. Maybe it's n log n. It was something like really crazy fast. Or you can go with, I think hierarchical plays really nicely with, if you have an idea of how many clusters that you want. You don't have to do a whole lot of parameter tuning in order to try and get some really nice looking clusters. Hierarchical will kind of be a lot better for that if you just kind of want to run it once and just kind of adjust the height of the thing. So that one's a good option for clustering as well. You need to have some kind of good distance metric or similarity metric. I think when it comes to text, for the metric that you're going to use in the distance thing, you're going to use, what is it, cosine similarity. Similarity. I heard it's technically not a distance metric. It's well, okay, so we'll just call it a similarity metric instead of a distance metric. Okay, and then for the classifier, so that one is going to not have a lot of data. We're going to say that it doesn't have a lot of data. So you can use, I would think maybe naive Bayes. You don't want to overfit. That's the issue here, is that we might get overfitting if we do something too sophisticated, like a neural network. Maybe you could use no, you don't want to use a support vector machine. There's cases where you have little data, and a support vector machine actually can be kind of useful. These support vector machines also work really well with small data. They don't scale very well though. So that's kind of why I was like, maybe a support vector machine is that, like, well, you don't really have any data here. But if we used too sophisticated of a kernel, it would obviously overfit. And then, well, somebody said decision tree when I was doing some reading, but I mean, if you only have like two data points, your decision tree is going to be kind of crap. Well, okay. Well, so if you have one interaction, you can look at the features of the article that they interacted with. So I guess there's a little bit more to it than that. So maybe maybe do decision tree, like I said. Or if you're really lazy, you can do a random forest. There's also gradient boosting machines. So if you're actually really serious about it and doing a classifier and you're doing something small that doesn't have a lot of data, like I said for CNN articles or Medium.com, gradient boosting machine. What is it, like XGBM boost? XGB. There's a really nice library out there for gradient boosting machines. Okay, would the user be able to add user-defined tags? Hold on. Chat got way ahead of me. Would the user be able to add user-defined tags? This should help train the model clustering, classification labels. Model more accurate, assuming people labeled their posts correctly. Well, so that would actually be metadata of the content itself. So that would be something that you would be able to make use of when you're doing your feature engineering. It would just be its own extra. You would what is it you would do with that? You would so if you can do multiple labels, I think you can do one hot encoding, or no, one hot encoding might be for enums. You would want to treat each individual thing, each possible tag as its own true or false true or false feature, and just flatten them all out like that, probably. But that's how you would handle that. But that would be like metadata of the feature itself. Metadata of the document itself, I meant. So maybe fair game, but usually with these kinds of problems, it would be you're going to be expected to also handle. You would need to handle stuff like TF IDF, stimming, stop words, stuff like that. So possibly fair, but also do these TF IDF, stimming, stop words. There's literally Python packages out there that just have a list of stuff like the, a, and, his. It'll just delete all those for you. And then you might even want to do PCA analysis and plus throw out the top few principal components as pure noise. Okay, what about taking the history articles a user read and check what cluster they are in and recommend a new article in the same cluster? Well, so that's if you have user history. That's if you actually have like a fair history of interactions. For content-based filtering, it's for when you have basically no interactions most of the time. This last one is for when you do have some interactions, and that is actually what you're capturing here, is such a history of articles. You have these pairs between a content record and your user information getting paired up. And so when you're doing your feature engineering, that's actually one of the things that you do for making the training data set, is that the interaction data is actually your history of articles. Article on a different cluster with smallest diff And so you're going to pull all the data into the same. You're going to pull all the data into the same thing. You might feel free to read up more on clustering if you have any concerns about that. There's tons of great content out there. I'd recommend the sklearn library, scikit-learn. I can write that really quick, but that is where I would recommend learning about that stuff. Okay, we're going to move on. Topic-based modeling approach would be best. Latent derelict allocation is a classic way of using unsupervised learning for finding topics. That is a term I have definitely seen before. I didn't manage to I get the impression you're probably 100% correct. I didn't get a chance to ever look into that a whole lot, but that does sound familiar. Learning for finding, yeah. So anybody else that's really interested in this, yeah, if I ever do a deeper dive into this specific variation, I'll probably be checking that out. Thanks for posting about that. Candidate generation, take entire items and reduces to 100K. This is the ranking step. Yep, that's what happens for, yep, that's the two-step process. Decision tree for ranking. Oh, okay. Yeah, that's a good point. So I did say ranking. You're right. That does seem rather absurd. I would think more of like something like logistic regression. Just a plain old regression is probably a better choice for ranking. Yep. Yeah, good call out. I have no idea why stuff that I read was recommending a decision tree for ranking. That sounds totally absurd. Is there a particular coding and CLV ecosystem you are using for your development? Well, so this is just like my personal laptop, and I'm just using Mac OS here, and I use it at work. I like using Mac OS a ton. And if you're doing machine learning stuff, you're probably going to see, PyTorch or TensorFlow. There's going to the data scientists are going to use Python. They're going to write some Python stuff, and then you can, if you just want to pickle it up, and then you can probably deploy it somehow on a different machine. I have no idea how the fancier. I've never worked with the fancy gradient boosting machine library. I've never tried TensorFlow or that other stuff. I think they run on like CUDA. Usually, when you deploy this stuff, when you're hosting an actual data model, the machine that actually runs the inferences, you're probably gonna have a GPU on it, from what I've heard. And then you can go ahead and use whatever language you want. Usually you can go ahead and host it in with Java or Golang or Scala or whatever you want. Otherwise, I'm also trying to get more into Docker and Kubernetes. That's a foreshadowing clue. I'm planning on getting a lot deeper into these problems as I'm starting to. I think we're gonna kind of like close it out in the next month or two. And then I'm gonna so I've already started redoing a couple of my problems like a lot deeper, particularly tinyURL and online auction. One of the things I want to do in the future is actually kind of revisit some of those and actually load test them on Kubernetes. That would be very cool. I would really, really like to do that. But yeah, so Docker and Kubernetes are things I'm really getting into lately for a development environment, and I would love to do some load testing of these and actually show how certain things actually are a bad idea or not. Okay, so that was the content-based filtering approach. Let's go ahead and do item-based clustering. So this is what Amazon's really well known for, item-based clustering. So it looks a lot, it looks really similar to content-based filtering. It's really easy to mix them up. I'm fairly certain that it would also do KNN or, hold on. So on this one, you would do clustering on, no, I know how this works. I know how this works. Yeah, okay. I have to like write this out. So I should definitely write this out. Should I write it out up there? Nah. Okay, so for item collaborative filtering, what you do is that you are going to find, you're going to calculate the similarity for every single pairing of the items. So for each item, find the distance to each other item, which is gonna that is kind of, it looks a lot like what you would be doing over here with this one. You're looking at the distance kind of, but instead of doing your feature engineering, the distance is going to be derived from is derived from features that use the user interactions. You don't actually have to know anything about the items that you're clustering, just what the users think of them, because you're going to use the similarity between users to create these features that you're not actually going to know anything about, like what those features represent. And you're probably also going to do some kind of it's another thing where you're probably going to have some kind of like embedding that you create, and you run PCA over it, and then your features are actually going to be like meaningless and not human comprehensible, I believe, because you're not supposed to actually know anything about the object itself. Like, so if you're trying to do recommendation of articles by topic, you should not actually be giving the model an understanding that certain ones are about economics as opposed to politics or something like that. It might do that internally, but you are not hard coding it to figure that out. It would only be able to drive that through the way that the users are interacting with those articles, not by anything in the text content of the article itself. So I think I had something up there that was really good at explaining this. Relies on similar users. I think I had something better. I have a different notepad on my other monitor. Okay, what did I write over here? This one's also supposed to scale a lot better than the user-based approach, and we'll get into that more as we're talking about the user-based approach. For given item, recommendations are the items scoring highest under the similarity measure. Similarity of the pairs determined by how users have rated the items. The ratings of the items by the users is the data, and the users are columns or features of the items serving as the rows or records. You know what? I'll go ahead and just copy paste this whole thing into the text file, and so that might help somebody else if I'm trying to comprehend this stuff. So yeah, the users are actually usually your users are rows. In this case, they're columns. They are actually features of your things that you're trying to cluster. Okay, with that, so we do need interaction data. We do still need that. So I guess we're going to take this. And so the model's actually not supposed to update very frequently with this. You're basically not going to have to ever update it because it handles users with little data or new users really well, to my understanding. So you have the content. It's host here. You pull up the page. You have your items over here. You still are going to have your interactions tracked, and those are still going to be fed into the data warehouse. That still is accurate. You do still have your interactions and your items over there that are going to get joined. And I don't think you really need to do feature engineering. No, you don't need to do feature engineering over here. You don't need to do TF-IDF. You might do matrix factorization. You might, yeah. So you could do matrix factorization, but there's other algorithms, and you're not doing feature engineering though. You don't have to do crazy stuff for cleaning up the data. You just like directly have this matrix of users mapped to items. Maybe it's like regularization. Would you? I think you might still kind of perform regularization, like, but for some of those algorithms, it's like while it runs. So then that would just kind of be like part of the model training. I think you don't really run any kind of cleanup stuff like as a separate process, I believe. For slope 1, so there's an algorithm for item collaborative filtering called slope 1, and it uses it does do some kind of adaptation to account for some users being a lot more mean in their ratings than other users, and that happens like during the training though. Okay, how it's doing a pair, it's calculating the distance between both of the pairs of items. And so what you're going to end up with is, okay, let's go ahead and write what we're going to have as an output of this. So we're going to have this gigantic table that's going to have item 1. Hold on. So we have item 1 is one column. You're going to have item 2 is the second column. You're going to have the score, which is like 0.74. We'll say that item 1 is 3456. We're going to have this one as 3670. And so then that is their similarity score that they have. And it's going to have n squared many records that are going to be put out by this, but you never have to change this. It relies on there being tons and tons of data on the individual items. So like, for example, with Amazon.com, you have thousands of ratings to an item, or tons of purchases, just lots of stuff to work off of already. But yeah, so you're going to have n squared many pairs. So that's the output. And so you can have it in a table, or like I did in the other one, I was like, if you already know what it's going to be every single time and it's not going to change, where did I do that? Where did I do that? Here it is. Yep, this is where I did that. So if it's going to be the same exact thing every single time, no, that's not. This is where I did that. Yeah. Because it was like your clusters aren't going to change. it only changes whenever you decide that the content needs to have the relationships updated, which is going to be a lot less frequent, as opposed to when you rely on user-based info, you need to update those models as soon as fresh user data is coming in, so you have to like continuously update the model. In this case, you can let it run stale for like a really long time. And so it's going to be similar to what we're doing in the item-based collaborative filtering. And that's why it's considered more scalable than user-based collaborative filtering. You don't have to rerun it all the time. You're able to just run it once, and then it is really expensive, and Squared is, that does suck, but you can let it go pretty stale. Okay. So we have the scores. So like okay. We're gonna grab, where's that? There it is. Yeah, we're gonna use this. It's pair ranking. It's some kind of similarity metric, or there's a couple of things out there for it. There was slope one, there was matrix factorization, couple of things that involve linear algebra and are just way beyond my grasp of mathematics. It's not a cluster DB, it is a, you can have it as just the ranking DB. It's just going to be the output here. Alternatively, there's another way that you can represent it. It's should I even do that in the other one? So you would just have the key of the item ID. So let's say it's 3456, and then you would have the pre-computed item list. Start it off with 3670, etc. So that's another way that I think it could kind of be represented, because you have a list that's in many items long that you're having come out of this, and it still is on whatever the training thing is, and so then you don't need the full list of n many items. You can just stick with the top 10 or 50 or probably 5, just however many you plan on recommending. Unless you're using this for candidate sourcing. If you're using this for candidate generation, then you might need the, well, even then you don't need the full n many records. You can then just bring it down to what, like 10,000, a few thousand, or a few hundred. You still don't need to use n squared many in the storage. You can bring it down to 100N, 1000N. Okay. Anyways, we got our database there. We don't need this. That's not actually being used anymore. And again, we've got PostgreSQL. And then you can go ahead and cache the pre-computed item list. You don't have a data model. You just have the pre-computed rankings of all that. You hardly ever have to rerun it. What was the sidecar deployment? Was that of the content? Oh, because there's, in the one case you had to do a full table scan. Yeah, you don't need that anymore. Should I do that trick in the other Redis database, item embeddings. Or no, it was, so you had the cluster ID. Oh, the idea was that it was just a really small amount of items per cluster, and so you didn't actually need to do any kind of trimming at all on it. Okay, I'm going to answer some questions, and then we can see if we can come up with anything else we can do with this, if there's any alternative approaches that are, I don't know, more interesting than whatever the heck I came up with here. Okay, what do we got? Tree for ranking. Is there a particular coding environment? That's good to mention. Item recommendations. If a user A comes to the service, it recommends items to A, which are similar to what A has liked earlier. Taking user feedback. Whoa, to understand. Yeah, yes, that's how the pair ranking worked, is that it's using those, it's using the likes of other people that are similar. So I think there was actually a really great article on it in Wikipedia somewhere that actually like kind of drew it out for slope 1, I think. Got it like over here. And I'll post the link into the chat and into the notepad. Come on. Yeah, so if there's a gap from somebody that didn't rate it, it's able to infer some kind of, it's able to predict the ranking or something. So that one was useful. I think that there was probably another useful one. It was probably item collaborative filtering. No, it wasn't. This one also is a form of item collaborative filtering, matrix factorization. And it also did not have a helpful table on it. I don't know where I saw the helpful table at. Yeah, so this one though was kind of helpful for trying to understand it. Here, I'm going to paste it over here in the chat if my computer will let me. There we go. Okay, move this and yep, there we go. Awesome. Okay. Is there anything else I was able to do with item collaborative filtering? We have our n squared list. We have our interactions. We have the items. I mean, I can pull out the CDN, but that's not really that. It's not really giving us anything drastically different. Yeah, no, I can't think of anything else that we can do that would be interesting here. So we can move on to user-based collaborative filtering. Yeah. Okay, I'm just thinking through that. So this one is definitely using a classifier. It actually uses, user-based. Okay, we can talk about this one a little bit more. So with user-based collaborative, the user-based approach, you see, what's it called? It's neighbor-based is another term for it. Neighbor-based, or what was it? It's going to use KNN, which is a type of classifier though. It's going to look at the K nearest users, and based on their rating of a specific item, it will use that to determine what the predicted value of the current user is going to think of that item. So it uses that and it just goes down the list of items that it's trying to recommend. It's whatever gives the strongest signal from KNN is the recommended items. What else do we have for, what model did I use for that? Oh, that one's weird. I still have no idea how to describe that. I guess it's kind of like a logistic regression. Yeah, I don't know any other approaches to it either. But you're doing pairwise ranking. That's all it's doing is pairwise ranking. Okay, I did talk about that one. Okay, KNN classifier. So we have the items, we have the interaction database, and so in this case we are instead going to be, so the records look a little bit different. You have these rows where it's maybe I can draw them a little bit like this. User A, you have user B, and then they are their rows. And then for the columns, you instead have like item A, you have item B, so those are the features. And so some of them are going to have rankings, some of them are not. And for whenever it's missing, you're just going to look at the K most similar users. So it's just users and items off of the interaction DB. I guess we don't even need to pull in a user table. That's what I was trying to figure out. I think the user ID is logged in the interaction DB. An interaction is just a pair between a that's a user ID combined with an item ID, and then it's some type of interaction. And so you would just have whatever interaction type it is right there. So it could be like an impression, it could be a click, it could be tapping on a like button, it could be the share functionality. There's so whenever people talk about the YouTube algorithm, and just you see one of the people running one of the big YouTube channels trying to tell you remember to like and subscribe or whatever, they're trying to get you to do one of the little interactions that'll send it a signal to put more impressions of their videos on your timeline. So it would be like a view, or you also have for item B, have let's say a share interaction, and then over here you have a view as well, or let's make it less confusing, you'll have like a like button or something. So that's the data you have, and you are clustering them over however you regularize these and make them comparable. So that would probably require some kind of special encoding if you have like multiple different things for what types of interactions are. Again, KNN classifier for this. Okay, and we're going to deploy that to a model store. You definitely want to use a model store for this. Get rid of that. Okay, and you would deploy the model to the pre-computed, nope, you would have a data model on them. It's just one. You don't have, you don't need the ranking service in this case, I think. Or, okay, so it's a given item. No, yeah, the data from the similar items is already kind of stored on it, and I think it uses like a KD tree or something like that. So you just have the sidecar deployed data model again. Okay, so you have your sidecar deployed classifier, Canaan classifier. Shoot, I guess you might need the feature store. You might use a feature store for converting a user into the proper embedding for that user. So it would pass over the user ID. You would translate it into some user features. Data model would take in that set of the current user's user features. It would find the K. It's already internal in the KD tree. It finds the K nearest users, the K most similar users, and it would then put out. Wait a minute, doesn't it need to? Oh, that does ranking. That does ranking, doesn't it? Because it's predicting what you would think of a given item. So you do need the user features, I think. So you are going to need a user feature store. Okay, so we're going to have the feature store, and it's not going to be S3. I think you can just go ahead and get away with some kind of like document DB. It doesn't even need indices on it. It like you can literally use MongoDB, or you can use, I don't know, DynamoDB. I don't know if you would want PostgreSQL. It's probably going to be read heavy. You're not really going to be updating the user features as much as you're going to read them, I believe. I mean, any document data store is going to be fine, though. And I said, like, even MongoDB is probably going to work just fine. So the request comes in. You're going to get the features for that user ID. I guess we can go ahead and write the schema really quick. So it's just going to translate the user ID of like 3467 into the user embedding, user features. Sorry, you can't see that. Yeah, so it's just kind of like a key value thing. I guess you could even use Redis. You could probably even use Redis. That would maybe even be a good idea if it's anything that's going to have half decent volume on it. And this one is going to, so user-based clustering allegedly doesn't scale as well as item-based clustering because it's going to need to continuously pull in fresh user data. So that's going to be important. You've got this steady stream of data coming in. to the interaction DB, you immediately stick it over there. I don't think you can do real-time streaming though. I don't think you can do real-time streaming of data. You just stick it over in the data warehouse and tell it to retrain the whole model. So I don't know how you can get better real-time training than this. I know that's like a thing that some of the ML ops people have, is this like real-time training feedback thing. It's really good for like reinforcement learning, or like a TikTok feed of videos. The TikTok feed of videos, it reacts to your user interactions really quickly. This is what I've got right now, so it's maybe a little bit less interactive than what they have, but there's probably a way to speed that up a little bit. So classifiers right there. You're going to have the user feature store. Let's talk about how that model is going to work. So you have the user features. It figures out the k closest users. I think you would have an item ID. You just need an item ID, and then it predicts what the value would be for that specific item ID. And so then that's going to go through your classifier, and it gives it a score or a rank. So that's what's in the data store. Let's draw an arrow so that you guys know where that refers to. Okay, but then how are you gonna get the item ID? Or so like don't you need to like run through the list of item IDs? Don't you need to like do a full table scan of all your item IDs available and like rank all of them? Yeah, there'd have to be, so you're predicting whether or not the current user would like this specific item, but how do you even know that this is an item getting recommended? You would have to do some kind of retrieval of a list of item IDs. And this is intended for, user-based clustering is intended for when there's, when you have more data about the users than the items. So there's not a lot of data on the items. Maybe it doesn't necessarily have millions of items. That seems rather absurd. It would definitely have a really bad, anything in collaborative filtering I think has a cold start problem. I'm thinking through how in the heck this thing's gonna work. So there's no way this is a good idea if there's millions of items. You don't want to actually have millions of items thrown at the data model and just rank the whole list of millions of them. So maybe you have millions of users with really heavy data, and then it's just thousands of items. And so then you can go ahead and have a sidecar deployed Redis instance with the list of item IDs that you're going to run through. So I'm going to mark that. So it'd be like Facebook. So then it'd be Facebook, where they're trying to recommend something a lot smaller number. Like if they're trying to launch their own video games, I saw YouTube's kind of trying to do that. But you wouldn't have a lot of content, you wouldn't have a lot of data on those items. And so if you have millions of users and you have thousands of these items, they're really not getting a lot of interaction. I feel like you have to do a full table scan of the entire Oh, I think somebody actually was saying something useful on this. 2A, which are similar to that. User recommendations. If a user A comes to the service, it recommends items to A, which are liked by other users similar to A. Yeah. Way to read from. Some feature store can ingest data from Kafka. I think hops works. Okay. Yeah, I have no idea how, because it has to like run down the entire list of the items, I think. So you basically have to do a retrieval of all the item IDs. Let's go ahead and throw the sidecar deployed Redis thing on there again. And again, this thing would go through the data warehouse. You don't want to have it run directly off of the OLTP. You don't want to copy that in a gigantic full table scan at once. So it should be continuously feeding that data into the data warehouse, and you're going to deploy a copy of that over to there during one of your service deployments. And then you would just run down the list of all the item embeddings with the data model ranking each one. You sort them. Maybe you can like pre-compute them, but if the users are just not interacting with it that regularly, I can see why it would maybe make sense to do that on the fly. Otherwise, this totally seems like another spot where you would probably just want to just take that trained KNN thing and then just run it down the entire item embedding list for all the active users, and then you would just serve that up cached instead of trying to run the data model live off of the service. But that is my best understanding of how you would do user-based clustering. Again, there's not really a whole lot of stuff that it seems like people are actually doing user-based clustering. It seems like it's mainly content-based filtering, maybe stacked on top of item-based clustering. Item-based clustering is supposed to be a lot more performant, I guess. And so when I was stuck on this, it was like, okay, well, I mean, I see why that would be really non-performant. I don't know if I was doing that correctly. This thing is what I got the impression was supposed to be the super expensive thing, but like, again, I don't know. I don't know how they would efficiently do this little trick right here on the ranking part. That just seems a little absurd. And again, that has a data model. So it would be a ranker, and you would need to have the GetRec service out in front instead of and this would be the ranking service. Okay, so your request comes, so you got the page loaded, now you want the recommendations. So you make a request to the recommendation service, which is stateless, and then you call the stateful ranking service that does its ranking of all the items. You return a response, then you send your response over to the user, your list of items that you are recommending. You'd probably do some kind of information retrieval trickery and just have a pre-computed list of items that are more relevant than usual, rather than trying to run the full table. That just seems so absurd. I'm done trying to figure out how in the heck that's actually supposed to work because I don't think anybody actually does user-based clustering though. Okay. You usually have a vector DB for that. That would totally make sense. You know what? That would totally make sense. I can see that. In the vector generation steps, the KNN search cuts down that number a lot. Yeah, well, so this one's just doing the ranking step. We're not trying to do the full ranking plus candidate generation process with the user-based clustering right here. We're not trying to do the two-step thing with this one. So that's why I don't have it with a second model or anything. But now I guess we can go ahead and get to the two-step process because I seriously have nothing else I can think of for trying to clean up the user-based clustering unless I added in the, I don't know, some kind of pre-computed Redis thing has a yeah, you'd just be stacking this on top of, I think, like item-based clustering for the trick that I'm thinking of, but it's like, well, you're basically doing the two-step process then. And so I just don't really want to draw it out if we're going to do that anyways. Really, okay, so VectorDB implements Canon really fast. Okay. That, yeah. Okay, I see why vector DBs are useful. That totally makes a lot of sense. Okay, let's move on to this two-step process. We've got, yeah, I didn't have anything specific called out for this, so we could just go ahead and go straight for it. So you're gonna have candidate generation, and then you would do the ranking. And what I had read is that you would do collaborative filtering for the first step, and then you do, so this is just straight from Alex Shu's book, is that YouTube does this. It's you do the collaborative filtering, step one, for the candidate generation. And then for step two, for the ranking, you're just going to do content-based filtering. And so this is where the fancier stuff from the content-based filtering column kind of came into play, is that this one's going to have a much smaller set after doing the candidate generation step. And then for this, I guess it was like item based. It was maybe it was either matrix based collaborative, matrix factorization. I think it was going to do matrix factorization. I'm just looking again at how the item based clustering actually works. Okay, yeah, we're gonna take this, we're gonna head over here, and I'm just filling this out so I can try and think through it all. And we've got user A and user B. Okay, you're comparing each of the items, you're scored or ranked. You can maybe do a pre-computed item list. No, that's a little Okay, I see how this could maybe get like reused even for like YouTube. That might be possible. Because it's this part's like not super personalized to my understanding. Okay, so I'm just gonna copy this one, and then we're gonna figure out how we can staple a content-based filtering model onto the end of the candidate generation step. Come on, come on. I said item-based clustering. So it's supposed to be item-based collaborative filtering. Sorry, that just got under my skin a little bit. Iterative filtering. There we go. Okay, and now we're gonna do 2-step variation. Okay, so we did the candidate generation part because we've got this thing already. It's the item-based collaborative filtering is there. Oh, isn't there a thing for the way that matrix factorization works where you're able to do, you just have the user embeddings, so you'd have so you have user embeddings, and then so you don't have video embeddings, but you have a video ID, and you feed that into the model, and then you would get the score or rank feeding in. But okay, right, because then you have your video ID that you have to feed into it, and so then you're just doing a traversal of all the video IDs. So this one, what I did here, so I already had all the items compared by the score. So in this case, we would have every video on, so this, for what the case that I'm the use case that I'm considering here, the concrete example that I'm considering is YouTube video recommendation, and I'm gonna almost definitely take another shot at this sometime within the next month or two after banging my head against the table a little more with my books. I'm joking. But so we got this. Every single video on YouTube would be compared with every other video on YouTube, which is a lot of videos. And you're going to want to have a partitioning key of whatever video it is that you just watched. Wait. You're able to feed the user embeddings into that. Right? So would you have that as part of the data table? Would you have that as part of the record on PostgreSQL? So you have item 1 and item 2 compared. Isn't it, so you run user embedding against the video ID and you rank that. How in the crap does that work for the matrix factorization. You know what? I'm not going to do the matrix factorization. We're just going to do pair ranking. We're going to keep this approach. And so instead, we just have every video on YouTube compared to every other video on YouTube. Partition by that. And then you're going to sort it by this. You're going to, well, so this is going to be the sort key, I guess. Because you kind of need to do that for the sort key. But this is going to be a secondary index. Okay. It's not PostgreSQL. It's like Dynamo DB or something like that. Yeah, I can't think of what else I would use. I still feel like it's going to be read heavy, so you're probably going to use DynamoDB. Oh, you could, yeah, maybe Cassandra actually makes sense here. You're probably actually going to write a lot of, yeah, I guess maybe that would make sense. Or it would be a vector DB. It could be a vector DB like Pinecone, like somebody was saying, since you're running through such a massive number of things. I don't know. This even looks kind of like an OLAP query. No, you're sorting by this. You're sorting by this and taking the top 10. That is, well, okay. But you've probably written a lot more records than you're going to read. I guess Cassandra makes sense here then. I think we're going to stick with that. Okay. So we're going to sort by score. We only need the item ID of whatever we just watched. We're going to sort the similar items to that by their score. We don't have this thing. You're not going to do a sidecar deployment of that. So you're fetching the top 1,000 or whatever records from DynamoDB here. There's no sidecar deployment. You're doing a fetch. Just like that. And this is the candidate generation service. You guys probably can't see this. Candidate generation service. Okay, so that's the first step, and then you're going to have the ranking. No, this is not ranking. This is the candidate DB. Okay, so we got that. Return the list of candidates, and then we are going to rank them. So for the ranking part, all right, so we're going to have a ranking service. Okay, and then how is that one going to work? So that one's, oh, that's right. It's going to do content-based collaborative filtering. That one is going to have content-based collaborative that one is going to have content-based filtering. And so you are going to have the user embeddings, and you're going to have video features. That's why it was video ID for the first one, is that you don't have video features. You only have the video ID to work off of. So this one is the one that's going to have user features. You're going to have video features. You're going to run them through the model, and then you're going to get a score or a rank. So this one is going to have, oh, no, okay. So that one is the candidate DB. No, okay, we do need that. We have two different models we're going to train. So that one actually does stay there. That one does stay there. We're going to have another thing that would get trained, though, for the content-based filtering. So we have another thing of, let's label this so that we'll actually remember what it is tomorrow. Okay, where in the heck am I gonna put this for the model store? So we're also gonna have model store. That one is S3. And then that one is going to get sidecar deployed onto the ranking service. Can like move this over to here. So this is the model that's going to be used for the ranking service. We can move this over here, I guess. And then we're going to have that. This one would need the feature store. This one's going to need, right, the user feature store, the video features. We would need it there, and then also this one's going to return video IDs. So you're going to need it on the ranking service and for the training. This little chunk right here wasn't even right. That's not even for the one up above. That's how it would work if I could figure out matrix factorization, but I can't, so. Okay, and we're gonna have this over here. That, we've got the model store right there. It's going to train the model. It's going to train, it's a classifier. Yes. Okay. So this one are, okay. Jesus. Okay. It is a classifier. It is a classifier. We're not doing, whatever the heck it was with the ranking. Yes, we have user features, and we have video features. We're going to have a model, and it's going to come out with a score or a rank. So you could do logistic regression is like one thing I've heard of, I think. Otherwise, you could actually do a neural network. What else would work for a classifier? Because you're trying to come out with like a score. I think that's probably going to be the best approach. Some kind of crazy neural network or a lot logistic regression. We have that, and then it's going to put it over in the model store. And then the model store can get deployed to the ranking service. Nope. Come on. There we go. When you do that sidecar deployment of the ranking service, you're going to drop off a data model. Just like that. There we go. So you get your list of video IDs. Oh, the feature store. That's what I forgot. You're also going to need your feature store. You're going to need that for this. And you're also going to have this thing's going to call it. Okay, so you want your recommendations. You generate a bunch of candidates from this thing that was pairwise ranked for whatever the last video you watched was. It returns like maybe 100 or 1,000 of those, passes them over to... Do we really need the candidate generation service? We kind of have a database for that. I'm going to leave it in there. Sometimes there's a model popped on there instead, and so I'm going to leave it on there for that reason. And then, okay, so you're going to return your list of IDs, item IDs, and then you're going to send those over to the ranking service. The ranking service is going to translate those into features for the individual IDs, the item IDs. Also for the user embedding. I think the user was already turned into an embedding. It wasn't just a user ID, I think. So I think that was necessary for candidate. No, it was not necessary for the candidate generation service. That's crazy. That might have been... That's probably why it's usually a model, is that somehow they're able to do something with the user embedding that would actually make sense. Okay, get those, send it over here. This is going to translate both the video IDs and the user ID into embeddings or their proper features. Going to run them through the model. This thing's probably running a GPU. You're going to score or rank for all of those videos, and you're going to return the top ones. And then you're going to return that over to the browser. There you have it. I'm just looking through my notes again to make sure I didn't do something stupid. Well, I mean, I definitely did do something stupid. I'm just trying to figure out if there's anything that can make it look less like that. No, I have that. Yeah, okay. All right, I guess that'll be enough for today. I'll drop a link for this into the chat. We're gonna save. All right, we're gonna export it to a link. I'm gonna paste it into the chat. Oh, I should also check if there's any comments in the chat. Come on, come on. Is it gonna paste? Is it gonna paste this thing? Maybe I just need a new computer. There we go. Now it's pasted. Okay. There's our conversation about PineConeDB. The matrix factorization calc takes every user in every video and checks the similarity dot product to the relevance for video for the user. Yeah, okay. Maybe it does just go ahead and run down the entire list of videos. That's just surprising. I don't know what else to say about that. Looks like matrix factorization only relies on user item interactions. Yep, it does. Yeah, I'm aware of that. Yes, matrix factorization does do that. There's some kind of you're technically, I believe, allowed to do. You can technically use user features. You can actually technically turn the user ID into user features, and it would still be considered collaborative filtering, and it still runs rather efficiently, allegedly. But I don't think matrix factorization does that. Looks like all embeddings are pre-calculated in the matrix factorization. Oh yes, yep, that's the trick. It turns the whole thing into does some kind of trickery with eigenvalues or eigenvectors, and yeah, I just suck at linear algebra. You can use two tower model. I saw that. I saw that in Alex Shu's book. I don't know what that is. I don't know what it means. I clearly, before I try to cover this problem ever again, I'm gonna have to read up on that. Yeah, I saw that though. I don't know what the heck it is. It's some kind of crazy neural net. He had like 3 other ones in there. He wasn't really great at explaining the inputs and the outputs to the model, which drove me crazy. I didn't like that he was not clearly communicating whether it was user IDs, video IDs, user features, video features, how in the heck it was going to get the video ID list. It was like, okay, is the model actually going to, is it actually trained to spit out a list of video IDs when you just hand it a singular video ID in? No, that's nonsense. Yeah. Well, yeah, I'm clearly gonna have to read up on that one more, but it seems like it was a step up. It seems like we had we still did pretty solid. I think we definitely have something to work off of. I think we definitely got something that we can work off of here. All right, I'm gonna wrap it up. Thanks for joining. I appreciate it. I already pasted the link into the chat. Thanks for joining me. This has definitely been an adventure. Yeah, I hope you guys had fun, and I hope to see you next time. All right, I'll let you guys go. See ya.